According to the 2005 National Electrical Code, the shield of a shielded conductor or cable must be grounded where used. However, there is an exception for shields that are part of an intrinsically safe circuit. In the scenario described, the shielded portion of the wiring should be grounded before the intrinsically safe portion, which includes the zener barrier or associated apparatus referenced in NEC section 504.2, and it should be grounded after the barrier. The reasoning behind this practice lies in the purpose of grounding the shield, which is to protect against electromagnetic interference, often referred to as EMI. Electromagnetic interference can introduce noise and errors into analog signals, potentially disrupting the intended operation of the system. Therefore, minimizing EMI is a crucial consideration in such applications. Grounding the shield before the barrier serves to prevent EMI from entering the intrinsically safe portion of the circuit. This is where the signal is most vulnerable to interference, and any noise introduced could cause significant problems. By grounding the shield before the barrier, you create a path for unwanted electromagnetic energy to be diverted away from the sensitive circuitry. Once the signal has passed through the zener barrier, the need for grounding the shield diminishes. The barrier itself is designed to limit the voltage and current that can pass through it, effectively preventing EMI from propagating into the non-intrinsically safe portion of the circuit. In essence, the zener barrier acts as a filter, blocking unwanted signals and ensuring the integrity of the signal. Therefore, grounding the shield after the barrier is unnecessary, as the barrier provides adequate protection against EMI. In summary, the grounding configuration should be such that the shield is grounded before the zener barrier to mitigate EMI in the intrinsically safe portion of the circuit, and ungrounded after the barrier as it is no longer required due to the barrier's protective function. This approach aligns with the requirements of the 2005 National Electrical Code and helps to ensure the reliable operation of the system. The 4.20 mA analog signal from a transducer that is signaling a programmable logic controller, abbreviated PLC, in this application is passing through a zener barrier, and the question concerns the appropriate location for grounding the shield. To elaborate further, the zener barrier is a safety device used in intrinsically safe circuits to limit the voltage and current that can flow into a hazardous area. This prevents the risk of ignition in potentially explosive atmospheres. The analog signal, which ranges from 4 to 20 mA, represents a measurement or control signal being transmitted from the transducer to the PLC. The PLC then uses the signal to monitor and control a process. The shield in the wiring serves to protect the signal from electromagnetic interference, which can be generated by various sources, such as nearby electrical equipment, radio transmissions, and power lines. Electromagnetic interference can corrupt the signal and cause errors in the PLC readings, leading to incorrect control actions. By grounding the shield before the zener barrier, any electromagnetic interference picked up by the shield is diverted to ground, preventing it from reaching the intrinsically safe portion of the circuit. This helps to ensure the integrity of the signal and the reliable operation of the system. After the signal has passed through the zener barrier, the barrier itself provides additional protection against electromagnetic interference. Therefore, grounding the shield after the barrier is not necessary, as the barrier will prevent any remaining interference from entering the non-intrinsically safe portion of the circuit. It's important to note that the specific grounding requirements for intrinsically safe circuits can vary depending on the application and the equipment being used. Therefore, it is always recommended to consult the manufacturer's instructions and the relevant electrical codes to ensure that the grounding is done correctly. In addition to grounding the shield before the zener barrier, it is also important to ensure that the grounding system is properly designed and installed. This includes using appropriate grounding conductors, making good connections, and ensuring that the grounding system is properly bonded to the building's grounding electrode system. A properly designed and installed grounding system will provide a low impedance path for fault currents to flow to ground, which helps to protect equipment and personnel from electrical shock hazards. In summary, the shield of the wiring should be grounded before the zener barrier to protect against electromagnetic interference in the intrinsically safe portion of the circuit, and ungrounded after the barrier as it is no longer needed. This approach, along with a properly designed and installed grounding system, will help to ensure the reliable and safe operation of the system. When dealing with intrinsically safe circuits, it is imperative to adhere strictly to the guidelines outlined in the National Electrical Code, specifically Article 504 and any other relevant sections pertaining to intrinsically safe systems. The National Electrical Code, or NEC, provides comprehensive requirements for the design, installation, and maintenance of electrical systems, including those used in hazardous locations. Article 504 specifically addresses intrinsically safe systems and provides detailed instructions on how to ensure their safe operation. Intrinsically safe circuits are designed to limit the amount of energy available in a hazardous location to a level that is below the ignition energy of the flammable materials present. This is achieved by limiting the voltage and current in the circuit to safe levels. Zener barriers, as previously mentioned, are commonly used in intrinsically safe circuits to limit the voltage and current that can flow into a hazardous area. These barriers typically consist of a network of resistors, zener diodes, and fuses that are designed to limit the voltage and current to safe levels. When installing intrinsically safe circuits, it is essential to use approved components and follow the manufacturer's instructions carefully. All components used in an intrinsically safe circuit must be certified as intrinsically safe by a recognized testing laboratory. The wiring used in intrinsically safe circuits must also be carefully selected and installed to ensure that it does not introduce any additional hazards. The wiring must be shielded to protect against electromagnetic interference, and the shield must be grounded properly, as discussed earlier. In addition to following the National Electrical Code and the manufacturer's instructions, it is also important to consider the specific hazards present in the location where the intrinsically safe circuit is being installed. This includes identifying the types of flammable materials present, their ignition temperatures, and the potential for explosive atmospheres to develop. Based on this assessment, the appropriate level of protection can be selected for the intrinsically safe circuit. Regular inspections and maintenance are also essential for ensuring the continued safe operation of intrinsically safe circuits. These inspections should include checking the wiring for damage, verifying the integrity of the grounding system, and testing the zener barriers to ensure that they are functioning properly. Any deficiencies identified during these inspections should be corrected promptly. In conclusion, installing and maintaining intrinsically safe circuits requires a thorough understanding of the National Electrical Code, the manufacturer's instructions, and the specific hazards present in a location where the circuit is being installed. By following these guidelines, it is possible to ensure the safe and reliable operation of intrinsically safe circuits in hazardous locations. The use of shielded cables in instrumentation and control systems, particularly those involving analog signals, is a common practice to mitigate the effects of electromagnetic interference, also called EMI, and radio frequency interference, called RFI. These types of interference can corrupt the signal being transmitted, leading to inaccurate readings, erratic control actions, and overall system instability. The shield in a shielded cable is a conductive layer typically made of braided copper or aluminum foil that surrounds the inner conductors carrying the signal. This shield acts as a barrier, preventing external electromagnetic fields from reaching the inner conductors and interfering with the signal. To be effective, the shield must be properly grounded. Grounding the shield provides a path for unwanted electromagnetic energy to be diverted away from the signal conductors and back to the source of the interference. This minimizes the amount of interference that can reach the signal conductors and corrupt the signal. There are different methods for grounding the shield of a shielded cable, and the appropriate method depends on the specific application and the type of equipment being used. In some cases, the shield may be grounded at both ends of the cable. This is known as a two-ended grounding scheme. In other cases, the shield may be grounded at only one end of the cable. This is known as a single-ended grounding scheme. The choice between these two grounding schemes depends on the frequency of the interference being encountered. At low frequencies, a two-ended grounding scheme is often preferred, as it provides better shielding effectiveness. However, at higher frequencies, a single-ended grounding scheme may be necessary to avoid ground loops. Ground loops occur when there are multiple ground connections in a circuit, creating a closed loop through which current can flow. This current can induce noise into the signal conductors, negating the benefits of the shield. In intrinsically safe circuits, the grounding of the shield is particularly critical. As discussed earlier, intrinsically safe circuits are designed to limit the amount of energy available in a hazardous location to a level that is below the ignition energy of the flammable materials present. Any interference that enters the intrinsically safe portion of the circuit could potentially increase the energy levels and create a risk of ignition. Therefore, it is essential to ground the shield properly to prevent interference from reaching the intrinsically safe portion of the circuit. As a general rule, the shield should be grounded at the non-intrinsically safe end of the cable, before the zener barrier. This prevents interference from entering the intrinsically safe portion of the circuit. The shield should not be grounded at the intrinsically safe end of the cable, as this could create a path for fault currents to flow into the hazardous area. In addition to grounding the shield properly, it is also important to ensure that the shielded cable is properly terminated. The termination should provide a good electrical connection between the shield and the grounding point. It should also protect the shield from damage and corrosion. There are various types of connectors available for terminating shielded cables, and the appropriate connector depends on the specific application and the type of cable being used. When selecting connectors, it is important to choose connectors that are compatible with the cable and that provide a good electrical connection. It is also important to follow the manufacturer's instructions carefully when terminating shielded cables. Improper termination can negate the benefits of the shields and can even damage the cable. In conclusion, the proper grounding and termination of shielded cables are essential for ensuring the integrity of signals in instrumentation and control systems, particularly those involving intrinsically safe circuits. By following the guidelines outlined in the National Electrical Code and the manufacturer's instructions, it is possible to minimize the effects of electromagnetic interference and ensure the safe and reliable operation of these systems. The principles of electromagnetic compatibility, often referred to as EMC, are fundamental to understanding the behavior of electrical and electronic systems in the presence of electromagnetic fields. Electromagnetic compatibility is the ability of an electrical or electronic system to function properly in its intended electromagnetic environment without causing unacceptable disturbances to other systems. In other words, a system is said to be electromagnetically compatible if it does not emit excessive electromagnetic interference and is not susceptible to electromagnetic interference from other sources. Electromagnetic interference, as mentioned earlier, is any unwanted electromagnetic energy that can disrupt the operation of electrical or electronic systems. Electromagnetic interference can be generated by various sources, such as electrical equipment, radio transmissions, and power lines. There are two main types of electromagnetic interference, namely, conducted interference and radiated interference. Conducted interference is electromagnetic energy that is transmitted through wires or cables. Radiated interference is electromagnetic energy that is transmitted through the air. To ensure electromagnetic compatibility, it is necessary to minimize both conducted and radiated interference. There are various techniques that can be used to minimize electromagnetic interference, including shielding, grounding, filtering, and proper cable routing. Shielding, as discussed earlier, involves enclosing electrical or electronic equipment in a conductive enclosure to prevent electromagnetic energy from escaping or entering the enclosure. Grounding involves providing a low impedance path for fault currents to flow to ground, which helps to reduce the amount of electromagnetic interference that is generated. Filtering involves using filters to block unwanted electromagnetic energy from entering or leaving a system. Proper cable routing involves arranging cables in a way that minimizes the amount of electromagnetic interference that is generated. In addition to minimizing electromagnetic interference, it is also important to ensure that electrical and electronic systems are not susceptible to electromagnetic interference from other sources. This can be achieved by using shielding, filtering, and other techniques to protect the systems from electromagnetic interference. Electromagnetic compatibility is an important consideration in the design and installation of all electrical and electronic systems. By following the principles of electromagnetic compatibility, it is possible to ensure that systems function properly in their intended electromagnetic environment without causing unacceptable disturbances to other systems. The National Electrical Code, or NEC, provides specific requirements for electromagnetic compatibility in certain types of electrical installations. For example, the NEC requires that shielded cables be used in certain applications to minimize electromagnetic interference. The NEC also requires that electrical equipment be properly grounded to reduce the risk of electrical shock and to minimize electromagnetic interference. In addition to the NEC, there are various other standards and regulations that address electromagnetic compatibility. These standards and regulations are typically developed by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the International Electrotechnical Commission, or IEC. Compliance with these standards and regulations is often required for electrical and electronic equipment to be sold in certain markets. In conclusion, electromagnetic compatibility is an important consideration in the design, installation, and operation of electrical and electronic systems. By following the principles of electromagnetic compatibility and complying with the relevant standards and regulations, it is possible to ensure that systems function properly in their intended electromagnetic environment without causing unacceptable disturbances to other systems.